who doesn't know what is vorticity?
Sir, I don't know.
Okay, excellent.
Sir, I don't know.
Perfect, perfect. Even one person saying no means we will freshly begin the things and go step by step. Excellent. Great. Any idea about global circulation, leaving apart about fluid mechanics, all these kind of things? The generic word like global circulation and so on, so kind of thing, atmosphere. Maybe in papers, newspapers, articles, magazines, whatever that. Have you ever heard anything about global circulation? It's a catchy keyword.
I recently read an article regarding how why Jupiter is hot, why it is not cold, despite being so far. So that is because of the heating effect of the auroras at the poles gets transferred to the equator.
I see. I see.
I think that is
Any
because
other?
of
Wonderful. What's your name, sir?
Prajwal.
Prajwal. Okay, wonderful. Because I can't see with whom I'm speaking unless I look at the tab. Fine. What about others? Maybe Snehal, maybe other guys heard anything about global circulation? Coral guys.
Sir, hello, sir. Sir, actually, no.
Okay, fine.
Circulation of air due to heat transfer.
I see. But what is circulation means?
Circulation means that local rotation of the fluid element.
Okay, fine, wonderful. So how about watching a short video about global circulation and its importance? Whether this circulation has any meaning, what it is, global and so on so thing. At least we will have some idea, rough. Okay, shall we begin? Great. Is it audible?
Is it that some parts of the world are warmer than others, even when they are approximately the same distance from the equator?
Guys?
Yes, sir, it was audible.
It was audible, okay.
Why is it that some parts of the world are warmer than others, even when they are approximately the same distance from the equator? For example, in the Scilly Isles that lie off the coast of Cornwall in southwest England, January temperatures are generally very mild. Frosts are extremely rare, and snow even more so. Average daytime temperatures are about 10 degrees Celsius, and nighttime about 5. Yet cross the Atlantic to the city of St. John's in Newfoundland, Canada, and the situation is very different. In January, there's an average 18 days of snow cover, and minimum temperatures at night average -9 degrees. That's a 14-degree difference between those two locations, even though they are at a similar latitude. One important factor is the Gulf Stream, a warm stream of surface water that circulates around the Atlantic Ocean. The North Atlantic Drift is an offshoot that circulates warm water around the Scillies, so the sea surface temperature almost never falls below 11 degrees in winter. In St. John's, at the same time, the sea temperature is 0.5 degrees. The Gulf Stream is partly caused by the circulation of ocean waters, but is mainly driven by winds. The Earth's climate, ocean currents, and global atmospheric circulation, or large-scale winds, are interconnected. At any one time, there are many different weather systems creating localized conditions around the globe. While storms are raging in the North Atlantic in February, in the Southern Hemisphere, Central Australia can be suffering intense heat, and heavy tropical rains might be falling in the Amazon rainforests. The global circulation model explains the Earth's atmospheric circulation. Heating and cooling effects around the globe are driven by wind. The starting point of this model is heat from the sun. Energy from the sun is shortwave light radiation and not actually heat. The heat we feel comes from light absorbed on the Earth's surface, which is converted into long-wave radiation that we feel as heat. So on a warm day, the heat we feel comes from the Earth's surface heating the air around it. Our location on Earth plays a major part in determining the amount of heat we feel. In the Sahara, during the hottest months, air temperatures can rise above 50 degrees Celsius. Over the course of 1 year, the intensity of solar radiation, or insolation, is greatest over the equator because the sun is directly overhead. At the polar caps, the sun hits the Earth's surface at a much lower angle, so the same amount of energy is spread over a much larger area, which means it's cooler. Polar ice sheets also reflect most of the sunlight that does reach the surface. There is an excess of heat at the equator and a deficit at the poles.
Let me ask you a few questions, guys. So are you in a position to follow the video, or is there any person who would like to have discussion, or perhaps would like to re-explain for the other friends? So Venkat, would you like to explain it to others what's going on?
Yeah, the question was like, even though the two cities or places are on the same latitude, why they were experiencing the different temperatures. So the answer was like, there was due to the temperature distribution, different temperature distribution among different areas. So there was a circulation, uh, air circulation around those different areas. So if in the example which we in the video which we saw, we can see that like hot air was going through the England, and then we can see that in the other part, like there was a cold air, so that's why we were seeing that kind of difference. And then
So if I understood you correctly, what you are trying to say is somehow on Earth, it's not just on land, but even at the oceanic level, there always be continuous circulations like hot, cold, this kind of differences. They will try to mix it up or transport so and so kind of heat or moisture, whatever these kind of things from one location to other locations. And they'll always be inherently connected with air, how that really flows over those kind of, perhaps leads to this difference in temperatures or so-called like rains and so on, so kind of. Is that right?
yes,
Sir,
sir.
sorry, sir. Hello.
Yes, one at a
Sir.
time. So one at a time, if someone would like to really speak, perhaps you guys may have to take permission from the other.
Sir.
Yeah,
Sir,
go ahead.
Sir, is it about Gulf Stream and other oceanic currents?
We will come back to that. Yes, that's also matters a lot.
Yes.
So at any place, whatever the thing we feel like heat, humid, moisture, rain, all these things ultimately connected in some sense with the oceanic circulations and also air circulation, what happens. And that's again ultimately connected with sun rays, how they are going to distribute. Okay. Hello.
Yes, sir.
Wonderful. So shall we go to the next one if this one is clear to everyone?
Yes, sir, it is clear.
Great. Wonderful. So let us look at next one. For example, the same thing, the 3D perspective. If we are trying to look at from space, especially maybe through satellites, how it really looks like. So basically here, we try to really look at from these satellites, these the crazy words like Meteosat, Geosat, these kind of crazy names, people try to use it based on certain kind of terminologies. And satellites help a lot in terms of understanding at least the 2D patterns, how do they really look like. And something like where exactly these typhoons are originated, one can really see it, where they are going, what kind of speeds they are rotating, and so on. So I think the satellites takes images using softwares, try to alter the colors and again send it back to ground stations, and again ground stations. What they do is they take either maybe through approximate methods, they will try to really understand how the direction of flow really happens, or they feed these kind of initial conditions to their models at the computers, try to churn out the system. Like you have pictures, you extract the data based on the color contrast and so on. The so-called algorithms really takes care of those stuff and convert that, apply it to something named GCMs, global circulation models, run that input data, finally get what might be happening in future. Maybe next 3 days, what will happen? Next 5 days, what will happen? And so on, so kind of stuff. And satellites provide enormous help. It looks like everything boiled down to fluid mechanics, but the reality is more challenging. One has to, I mean, like whoever's going to work on these atmospheric flows, they have to be good with fluid mechanics, they have to be good with algorithms, they have to be good with electrical technologies, they have to be good with electronics, signal communications, manufacturing. Thousands of areas really flourish just because of this atmospheric circulations. And people usually work on that. And if you are, now let us look further about this atmospheric circulations. Something more about global circulation, let us look at it. We understood there might be something like sun rays are falling on that, and perhaps at equator, more heat really distributed, it will be warmer, it might be rising, maybe oceanic circulations really start traveling or moving from that equator towards other locations and so on. But now the question really comes, why a lot of guys, am I audible?
Yes.
Yes.
Yes, sir.
Okay. So why those sun rays really fall a lot on equator? Why less on polar, perhaps spreading out that? Is there any connection with Earth rotation? That's the thing what we are going to really look at.
The last video showed that different parts of the Earth heat up differently, with the equator receiving more radiative heat from the sun from the poles. And the purpose of global circulation is to redistribute this heat. If the Earth did not rotate and was a simple landmass with no oceans, we would have a single circulatory cell in each hemisphere, where hotter air would rise at the equator and flow toward the poles. The air would sink as it cools and then return towards the equator. But the unequal distribution of land and ocean and the speed of the Earth's rotation make this circulation system more complicated, giving us a three-cell pattern which exists in both the northern and southern hemispheres. The largest cells are the Hadley cells. At the equator, the warmer, less dense air rises. It rises to a height of about 18 kilometers and spreads out underneath the tropopause. The tropopause acts as a lid to the lowest part of our atmosphere, which contains all of our weather. The warm air spreads out towards the poles, gradually cooling and sinking as it moves. before descending to the surface and flowing back to the equator. The smallest cells are the polar cells. Cold, dense air descending in the polar regions flows at low levels to about 60 to 70 degrees north or south. As the air leaves the polar regions, it starts to warm and rise, returning to the poles at high levels. Between the Hadley and polar cells are the ferrule cells. Unlike the other cells, the ferrule cells are not driven by temperature. These cells flow in the opposite direction to the Hadley and polar cells, acting like a gear. These circulating cells not only transport heat from the equator to the poles, but also result in semi-permanent areas of high and low pressure due to the rising and descending parts of the circulation cells, giving us our climatic zones. Where air is rising, an area of low pressure is created. So these areas see much more rainfall. This is why the largest areas of rainforest are found near the equator, and why the United Kingdom has a relatively wet climate. Where air is descending, an area of high pressure forms, giving largely clear skies and little rainfall, which leads to the desert regions. But not all deserts are hot. Antarctica sits under the descending branch of the polar cell and is also classed as a desert. With more precipitation falling in the Sahara, Antarctica is the largest and driest desert overall. Check out our video on atmospheric pressure for more on how pressure leads to weather. Our next video shows how the rotation of the Earth gives us jet streams and prevailing winds.
Okay, let me ask you a few questions, guys. Maybe Avirup or Amarjeet or anyone. How many kind of circulations are there, cells?
Sir, 3 type.
What are they?
Hadley cell and polar cell. And third is between them, I am forgetting, sir, sorry.
Ferrule cell.
Ferrule.
Wonderful. Ferrule cell, wonderful. First of all, tell me why anyone will see such kind of cells. How the mechanism really works, at least for Hadley cells.
Due to solar insolation is more at equator, the air around the equator due to low pressure it rises and moves towards the tropopause and gets structured there, and then after reaching to the latitude about subtropics, it descends after cooling. Then due to Coriolis force again it comes back to towards equator, completing a loop.
I see. Okay, let me simplify because you must be from Coral department. These words like tropopause, stratosphere, and so on, so things still we have to learn. So let me simplify if I understood you correctly, because sun radiation is falling on Earth, especially at the equator, and whatever the air that becomes warmer because it's grabbing heat, it becomes buoyant enough. The density really drops down by increasing temperature for most of the typical gases. So that becomes lighter in density. And Earth completely surrounded by atmosphere, and gravity is pointing towards the center of the Earth. So any part of that Earth, if you are going to take it, because it's a spherical geometry in some sense, so whatever the air really get warmed up, it wants to rise. Usually rise means we really look at our local coordinates, but for Earth, rise means go away from the Earth in the radial directions, especially at the equator, because gravity is trying to pull, but because it becomes lighter, buoyant enough, it wants to really rise or move away from the Earth. And this atmosphere always be pulled by the gravity. So it can't go forever into that space direction. Gases are very difficult to escape from atmosphere, something like 100, 200, 300 kilometers. Beyond that, they can't really go. While these gases expanding, becoming lighter and so on, so thing, because all about is having heat so that they are lighter. they try to rise. But at the same time, space outside one is cooler. Though solar radiation is falling on that, they won't carry any heat other than energy, the photonic kind of energy. Heat, what we actually call is the low wavelength kind of thing. Usually you may not really see, but long waves are really coming. They are slightly cooler outside atmosphere. So whatever the heat these rising gases are going, they ultimately cool, so they can't go further. At the same time, there might be cold zones which are trying to fall down. So that's going to really set up something like a circulation. Because of this earth rotational kind of things, there will be stable, unstable equilibria really associated with that, which again we will come back at later part of the classes. What we will see is something like these circulations. Similarly, at poles which are lighter, cooler, heavier, cooler in that sense, they will have a specific kind of motion. They can't really show like a tropical kind of thing. Guys, am I audible? Hello?
Yes, sir.
Yes,
Yeah.
sir. Yes, sir.
Because sometimes I'm losing this network connection. So the colder ones, they show different kind of instability. If you are looking at Hadley cells, they rise from equator, goes, takes a turn, come back. Whereas the polar cells, they show different kind of equilibria, like they will rise from the sides, sink at middle, and so on, so kind of thing. So topologically, they will have different kind of structures. And when these polar cells, Hadley cells, though the crazy, so many new words what we are trying to learn, because of this circulation, their instabilities and so on, there will be one more cells happen like Ferrel cells. And these are not driven by your temperature differences, but because of these circulations, going to generate one more gear kind of thing. Again, this gyre motions and so on, again, we will learn new about that. Because of these two circulations going to drive and make the weather to complete. And again, something like a new words like what we have learned, the person has said like latitudes and so on. So on Earth, if you are trying to look at the horizontal lines, what you are trying to construct are called latitudes. And around that, if you are going to wobble around the length, pole to pole, if you are going to connect, you will call like longitudes. Altitude is locally you stand on Earth, try to look it in the upward direction. So something like latitudes are circular ones, longitudes are also circular, but connects the poles, divide the Earth into that direction. And because of the sun rays falling onto that particular belt like equatorial belt and so on, more amount of heat really enters into atmosphere. That is the story of that. Let us look further.
Excuse me, sir. Sir,
Yes, sir.
sir, I have one doubt, sir. Sir, you said that because the poles are on the top, the sun rays they fall over a greater area, so that's why the temperature is less as compared to equator. Sir, but the Earth's axis has a tilt rate of 23.5 degrees.
Precisely. The equinox effect is the most important thing. It's not about just how these rays fall, but especially the tilt angle of the Earth is the one which makes all this story different. Over that, it's not about just sun rays directly falling on the system, how quickly they will reflect out of the system also. That's also going to really affect the system, because your equator kind of things, you do not have any ice or white kind of patches. So the reflection becomes so difficult, they will have a tendency to absorb that. Whereas poles or somehow created this kind of, why these ice are forming, that's completely different story. But because these ice layers have a susceptibility to reflect back a lot of solar radiation, you will have less amount of heat grabbed into the system. In some sense, all these things usually people attribute to the Earth inclination angle, which we will shortly see. Okay, shall we go?
Yes, sir. Thank you, sir.
Great.
The equinox is defined as the instant in which the midpoint of the sun crosses the Earth's equator. This occurs twice a year in March and September. Following the March equinox, the northern hemisphere begins to tilt towards the sun and astronomical spring begins. This is known as the spring or vernal equinox. At the same time, the southern hemisphere will start tilting away from the sun because this is their autumn equinox is derived from the Latin word for night. However, day and night are not precisely equal on either the spring or autumn equinox. This occurs on the equilux, the date of which varies depending on location. Typically, the equilux is around 2 to 3 days before the spring equinox and around 2 to 3 days after the autumn equinox. There are two main reasons for this. First, imagine the sun were a single point in the sky. On the equinox, the time taken between the sun crossing the horizon at sunrise and then again at sunset would be exactly 12 hours. However, the sun doesn't appear as a single point in the sky, but as a large disk. And sunrise is defined as the moment the top of the sun's disk appears above the horizon and not its midpoint. Later, sunset occurs when the top of the sun's sphere appears to dip below the horizon. The extra time in which only the top half of the sun is visible above the horizon adds around 2.5 to 3 minutes of daylight at mid-latitudes. Second, sunrise and sunset are based on the appearance of the sun above the horizon and not on the sun's exact geometrical position. This is significant because of an effect known as atmospheric refraction. The variation in density of the atmosphere allows it to act like a lens or prism, bending sunlight above the horizon. This means that when the sun first appears in the sky at sunrise, it's actually still below the horizon. Atmospheric refraction adds around 6 minutes of daylight to locations in the mid-latitudes, but its effect varies depending on the weather. Lower temperature, higher humidity, and higher air pressure results in more atmospheric refraction and a slightly longer day. The date of equinoxes also vary year to year from 19th to 21st of March and 21st to 24th of September. A year isn't exactly 365 days long, but just under 365.25 days. This causes the equinoxes to drift later by around 6 hours every year until a leap year occurs.
One more crazy word what we have to know is mid-latitudes, because most of this atmospheric research are flourished by UK, European kind of system at one point of time. So if you open textbook and so on, so thing, their preference is always given to mid-latitudes. Are the ones, the zones which are covering this UK, Europe, perhaps top side of that Russian belt, Japan, and so on, so kind of stuff. And we are at India, in some sense, close to equators. We are not precisely on the equator, but the zone like something like we call 23 degree kind of line, top and bottom kind of thing. That zones on the earth, what we call equators zones. Above that, on that equatorial, above that equator, we call mid-latitudes, from the 23 degrees all the way to some 60 degrees and so on, 70 degrees kind of thing. Again, from the 70 to 90 degrees on the polar zones, we call basically these polar regions. The weather systems, the climate, what you are, okay, loosely I'm saying that the basic weather patterns in some sense depends on whether you are on the tropics or equator kind of zones or mid-latitudes and by above that polar zones. These three weathers in some sense different, because at that mid-latitudes mostly is governed by fluid mechanics phenomena rather than heat and other kind of moisture kind of environments. That's also one of the reasons tropics in some sense have complex structure like heat, moisture, fluid mechanics, and many kind of things. Let us look at, leave apart about this earth. All the time earth is very boring weatherman kind of thing. Let us look at how complicated this atmosphere flows on other planets. So any idea about sun? Quickly.
While billions of stars are scattered throughout the universe, the one at the center of our solar system plays a special role for us here on Earth. Our sun formed about 4.5 billion years ago in the Milky Way galaxy's Orion Spur. It was born when a cloud of dust and gas, known as a solar nebula, collapsed. And in the middle of this formation, matter condensed into a burning ball of gas that became our sun. The sun's fiery nature, along with a tremendous gravitational pull and an extensive magnetic field, helped it to become the heart of our solar system. The sun can be divided into 6 layers or regions: the corona, the chromosphere, the photosphere, the convective and radiative zones, and the core. In terms of atom count, the sun is about 91% hydrogen, the sun's fuel, 8.9% helium, and 0.1% heavier elements such as carbon and nitrogen. Due to the sun's extreme temperatures, these elements stay in a gas-like phase called plasma. In the core, temperatures reaching at least 27 million degrees Fahrenheit, combined with the sun's powerful gravity, fuse together hydrogen molecules to create helium. Called thermonuclear fusion, this releases an enormous amount of energy in the form of radiation, electricity, solar wind, and, as we experience on Earth, life-giving heat and light. Such volatility is contained thanks to the sun's tremendous gravity. It's strong enough to hold the solar system intact and is primarily due to the sun's size and mass. Our sun is the largest and most massive object in the solar system. It's more than 100 Earths wide and could theoretically fit all 8 planets inside nearly 600 times. It also contains approximately 99.8% of all the mass in the solar system. Because of this mass, the sun has a great pull on the fabric of space, creating a gravitational force that causes nearby planetary bodies to be drawn toward it. This gravitational pull allows the sun to hold together a system of 8 planets, potentially dozens of dwarf planets, at least 170 moons, and countless comets and asteroids. Without the sun's gravity, these celestial bodies would drift off into deep space. Another critical property of the sun is its magnetic field, which encapsulates the entire solar system. Called the heliosphere, this force field protects the planets from harmful cosmic radiation. It's caused by the sun's plasma pushing electrically charged particles toward the star's poles. This process turns the sun into a giant magnet. Although the sun's magnetic field is invisible to the naked eye, its effects are noticeable. On the sun's surface are dark areas called sunspots, which mark strong pockets of magnetism. On Earth and on some of the other planets, the sun's magnetic field interacts with their atmospheres, resulting in beautiful auroras. Despite its size and strength, the sun will not last forever. In about 6.5 billion years, it will run out of its hydrogen fuel, expand to envelop Mercury, Venus, and even Earth, and then collapse into a small star known as a white dwarf. In the meantime, the sun will continue to play a critical role in the system that bears its name. The sun's protective magnetic field, tremendous gravitational pull, and ability to create vast amounts of energy will protect, contain, and give life to our solar system.
So when you are looking at sun, the problem is more complicated than what we are trying to target, like atmospheric flows. So let us move on to next planet. What about Jupiter? Do you have any atmospheric flows on Jupiter?
Yes, sir.
Red
So
spot.
there's a very great red spot. There's a huge storm going on.
Wow. Okay, let us look at that.
Born from primordial stardust 4.5 billion years ago, Jupiter was the solar system's first planet. And much like its namesake, the king of the ancient Roman gods, Jupiter was destined for greatness. Jupiter is the fifth planet from the Sun and the largest planet in the solar system. At approximately 11 Earths wide, Jupiter has twice the amount of mass as the other planets put together. But unlike Earth and the three other terrestrial worlds, Jupiter has no solid surface. It may not even have a traditionally solid core. Rather, this giant planet may have a dense liquid center surrounded by a worldwide ocean of hydrogen and helium gases. Jupiter's gaseous composition can be observed in its atmosphere. About 44 miles thick, the atmosphere is a canvas of stripes and storms churning across the giant planet. Their colors range between shades of whites, yellows, browns, and reds, all caused by the different chemical makeup of each area. Probably the most iconic feature of Jupiter is a crimson-brown storm that's been raging for over 300 years, the Great Red Spot. It's a giant swirling collection of clouds with wind speeds of up to 400 miles per hour, at least 2.5 times faster than Category 5 hurricanes. Floating hundreds of miles above the storms of Jupiter are about 79 moons, the most of the 8 known planets. The 4 largest moons were discovered by Galileo in 1610. Called the Galilean satellites, they include Io, the most volcanically active celestial body in the solar system, Ganymede, the solar system's largest moon, even larger than the planet Mercury, and Callisto and Europa, which, along with Ganymede, may contain oceans of liquid water underneath their crusts. Jupiter's large collection of moons is only made possible by the planet's massive size and gravitational pull, the strongest of all the planets in the solar system. This incredible gravity also influenced the sizes of the 7 other planets. During the solar system's earliest days, Jupiter, being the first planet to form, attracted and destroyed space debris that would have helped the other planets grow in size. Today, that force may serve as a shield by attracting comets and asteroids onto Jupiter's own surface, preventing them from crashing onto inner planets like Earth. Apart from the Sun, Jupiter has become the dominant figure in the solar system, thereby earning its place at the top of the planetary heap as king.
Great. Let us close today's session with one more video. And first few classes, we are first of all trying to have feeling about flows. How large are they? We are not jumping into any mass or crazy terminologies. First of all, more like a wanderer, like Sanchari, we are trying to really looking at what's going on with this entire big system. Okay, let us look at Saturn.
With its gold color and stunning rings, Saturn is quite a planetary gem. Saturn is the second largest of the 8 planets, and it is about 10 times as wide as Earth. Despite its size, Saturn is actually the lightest planet. It is predominantly made of the gases hydrogen and helium, and because of its particular gaseous composition, Saturn is the only planet in the solar system that's less dense than water. If the planet were placed on an enormous ocean, it would be able to float. Saturn's gaseous makeup also means that it has no true surface. At its center, the planet has a dense core of water, ice, and rocky material, but it has no actual landmass. Instead, it's mostly made of gases, liquids, and yellow ammonia crystals that swirl around the planet, creating golden clouds and storms. The largest storm on Saturn is at its north pole. It's over twice the size of Earth and shaped in a near-perfect hexagon. Each of the 6 sides is believed to be the result of jet streams, which all encircle a massive hurricane. Because of Saturn's inhospitable environment, the planet cannot support life, but some of its moons might. Saturn has more than 50 confirmed moons, and each varies in size and terrain. Enceladus, one of Saturn's smallest moons, is covered in ice and only about as wide as the state of Pennsylvania. Titan, Saturn's largest moon, is nearly as wide as Canada. Titan is also the only moon in the solar system with clouds and a dense atmosphere. Both Titan and Enceladus have underground oceans that would make them potentially capable of sustaining life. Saturn's moons may also play a role in shaping the planet's signature feature, its rings. Saturn's ring system is the largest and most complex in the entire solar system. The rings are made of icy and rocky remnants from comets, asteroids, and moons. The particles range in size from being as small as dust to as big as mountains. The ring system is divided into 7 groups of rings. Altogether, they are as wide as 4.5 Earths, but only about 2/3 of a mile thick. How the rings are able to stay on track and intact has to do with Saturn's smallest moons. Called shepherding moons, these tiny satellites orbit between the rings, and they seem to use their gravity to shape the ring material into circular paths. Saturn has fascinated scientists and amateur astronomers alike for thousands of years. The ancient Greeks and Romans, who named the planet after their god of agriculture, believed it was a star. It wasn't until the 17th century, after the telescope was invented, that scientists like Galileo Galilei, Christian Huygens, and Giovanni Cassini could take a much closer look. Only then was Saturn's planetary status discovered, and ultimately its many moons and brilliant rings. Because of its planet-like moons, lightweight composition, and dazzling ring system, Saturn continues to mesmerize us to this day.
Okay, I'm really sorry because we are talking only about European scientists and so on, not about Indian or Asian kind of things, because these videos are made by them. So we are not actually touching that kind of science. And do I have more time or am I done?
Sir, I had CFD class.
So let us close this session. Okay. See you in the next class.